It weighs less than a paperclip. It's the most swatted creature on Earth. One slap ends its whole existence instantly. Now give it 99.999% of the speed of light. A mosquito, at light speed, carries the energy of a nuclear weapon, not a bite. That's not a metaphor. That's the actual physics, and it's about to get stranger than the sentence makes it sound. You've swatted a mosquito before. Everyone has. It's an automatic gesture, barely a thought, the smallest possible act of violence a human being performs on a near-daily basis. The insect weighs somewhere between 2 and 2.5 milligrams. That's less than a single grain of rice, diluted down by a factor of 100. Nothing about that number suggests danger. Nothing about that mass has ever, in the history of mosquitoes, threatened a city. Now strip away the SWAT. Instead, picture that same mosquito, same size, same negligible mass, closing in on you at a fraction of light speed, so close to the maximum that the difference barely registers as a number. It doesn't bite you. It doesn't even reach your skin in any way you'd recognize as an insect landing. Before it crosses the last few meters of open air, the atmosphere around it ignites. Not catches fire. Ignites, violently, all at once, in a fireball that erases you, your street, and everything for kilometers in every direction. One insect. No explosives, no chemicals, just speed. Here's the part that should stop you before the details even arrive. Nothing about the mosquito changed. Not its mass, not its shape, not a single physical property of the creature itself. The only variable in this entire scenario is velocity. And velocity alone is enough to turn a housefly-scale nuisance into something indistinguishable from a nuclear strike. Hold on to that thought. Einstein's special relativity says something uncomfortable about how energy and speed relate to each other. In ordinary experience, kinetic energy behaves the way common sense expects. Double an object's speed, and its energy goes up by a predictable, bounded amount. A faster truck hits harder than a slow one, but the increase feels proportional, reasonable, something your intuition can track without help. That intuition works fine almost everywhere in daily life. It completely stops working once velocity climbs into territory close to the speed of light. Special relativity introduces something called the Lorentz factor. It's a multiplier that describes how dramatically an object's effective energy increases as its speed approaches light speed. At everyday velocities, this multiplier barely differs from 1. It might as well not exist. But as velocity keeps climbing closer and closer to light speed, the Lorentz factor doesn't increase gently. It explodes. It grows without any upper limit, mathematically approaching infinity as velocity approaches the speed of light itself. This is exactly why nothing with mass can ever actually reach light speed. The energy required to push an object that final fraction of a percent faster grows without bound. Get close enough, though, and you don't need infinite energy. You just need an amount so large it barely resembles anything from ordinary experience anymore. At 99.9999% of light speed, 6 nines of precision past the decimal point, the Lorentz factor for any object reaches approximately 707. That number applies to a mosquito exactly the same way it applies to a truck, a bullet, or a planet. Mass doesn't change how the multiplier works. It only changes how much raw energy that multiplier gets applied to. Here's where the mosquito stops being a joke and starts being terrifying. Multiply its tiny rest mass energy, the baseline energy locked into its mass by Einstein's famous equation, by a factor of roughly 707, and you're no longer talking about insect-scale numbers. You're talking about energy in the range of tens of megatons of TNT equivalent from an object with less mass than a paperclip. For comparison, the Tsar Bomba, the largest nuclear weapon ever detonated by humanity, released roughly 50 megatons. A relativistic mosquito sits comfortably in that same range, sometimes exceeding it, depending on exactly how close to light speed you push it. The same creature you'd swat without a second thought, moving fast enough, rivals the most destructive weapon our species has ever built. Sit with that gap for a second before the mechanism gets explained. The instinct almost everyone carries reasonably is that destructive potential tracks with size and mass. A truck is dangerous because it's heavy. A bomb is dangerous because of the chemicals or fissile material packed inside it. Velocity, in this mental model, is just a modifier, something that makes an already dangerous object a bit more dangerous, not something capable of overwhelming mass entirely on its own. That model isn't wrong at everyday speeds. It's completely wrong at relativistic ones. Newtonian physics, the version of motion you learn in school, treats kinetic energy as scaling with the square of velocity. Already, that's more dramatic than most people expect, since doubling speed quadruples energy rather than just doubling it. But even that relationship stays bounded, predictable, comparable across normal ranges of speed. Special relativity replaces that relationship entirely once velocity gets close enough to light speed. The Lorentz factor doesn't just add a multiplier on top of the Newtonian formula. It takes over the entire calculation. Once you're within a whisper of light speed, the energy equation stops caring almost entirely about mass and starts being dominated, almost exclusively, by how close to the limit you've pushed the velocity term. A mosquito at 99.999% of light speed isn't a slightly more dangerous mosquito. It has stopped being meaningfully describable as a mosquito at all, in terms of its physical effect on the world. It has become, functionally, a relativistic kinetic energy weapon, where the mass that used to define the object has become almost irrelevant next to the velocity driving the energy calculation. This isn't theoretical guesswork built on extrapolation alone. Humanity has already tested this exact relationship, just at a different mass scale. Since 2008, physicists at CERN's Large Hadron Collider outside Geneva have been routinely accelerating individual protons to approximately 99.9999991% of light speed. At that velocity, protons reach Lorentz factors exceeding 6,900. The collision energies produced, measured in trillions of electron volts, have been documented, confirmed, and repeated thousands of times under carefully controlled conditions. The physics isn't speculative. It's measured, verified, and published. But a single proton carries a mass roughly 10 to the 19th power times smaller than a mosquito. That's not a small gap. It's the difference between something almost too small to imagine and something you can watch fly across a room. The energy gap between accelerating a proton to relativistic speed and accelerating a visible insect to a comparable speed is staggering, precisely because the Lorentz factor multiplies whatever mass it's given, and a mosquito hands that multiplier vastly more raw material to work with than a proton ever could. This is where the failure chain begins in earnest. Once that mosquito reaches the edge of your street at close to light speed, it doesn't slow down gracefully or bounce off the first air molecule it meets. It collides, immediately, violently, and the energy it's carrying doesn't distribute gently across the surrounding atmosphere the way a normal high-speed impact would. At relativistic velocities, a collision with ordinary air molecules doesn't behave like an impact at all, in the conventional sense. The kinetic energy gets deposited into the surrounding atoms with such extraordinary violence that it can trigger reactions inside those atoms resembling nuclear fusion momentarily at the point of contact. The mosquito isn't hitting the air the way a bullet hits a wall. It's briefly turning the air itself into something closer to the interior of a star. That energy release, concentrated at a single point, doesn't stay contained to that point. It radiates outward as blast wave, thermal radiation, and shock wave, propagating through the atmosphere exactly the way energy from a nuclear detonation does, because at this scale, the physical mechanism producing the explosion genuinely resembles a nuclear one, even though no nuclear material was ever involved. Here's the scale jump worth sitting with directly. 2.5 milligrams, something so small a light breeze could carry it sideways, becomes the trigger for an event capable of leveling an entire city block, potentially far more than that depending on exact velocity and altitude of the collision. The mass never changed. The destructive radius went from 0 to kilometers, purely because of what velocity does to the energy equation once you're close enough to the limit. A viewer might reasonably ask here whether some kind of shielding could handle this. After all, engineers build systems to survive meteorite impacts, high-velocity debris, even small-scale explosions. Surely something exists that could absorb or redirect this kind of energy. It doesn't, And the reason is straightforward once you look at the scale involved. Conventional shielding, whether for meteorites, ballistic impacts, or industrial explosions, is engineered around energy levels that, while significant, remain many orders of magnitude smaller than what's being discussed here. Even a large meteorite strike, capable of leveling a city on its own, involves energy levels that are dwarfed by tens of megatons concentrated into a single point of impact. No material developed by human engineering, no armor plating, no blast-resistant structure is designed for or capable of meaningfully absorbing an energy release comparable to a large nuclear detonation happening at a single, near-instantaneous point. The entire discipline of impact shielding assumes energy scales far below what a relativistic mosquito would deliver. The fix simply doesn't apply because it was never built for a problem at this magnitude. This is the point of no return in the failure chain, and it arrives almost instantly, within a fraction of a second of the mosquito crossing into the atmosphere near you. Once the collision begins, there is no intervening moment where the outcome could still be altered. The energy transfer happens too fast and too completely for any physical response, human or mechanical, to matter at all. There's a genuinely strange irony buried inside this scenario, one that's easy to miss underneath the raw destruction. The mosquito itself, as a distinct object, effectively ceases to exist as a mosquito the instant this collision begins. Not because it's fragile in any ordinary sense, because at these energy levels, the question of whether the mosquito individually survived the impact stops being physically meaningful. It has been converted, essentially instantaneously, into pure energy and shockwave, indistinguishable in outcome from any other object carrying the same relativistic kinetic energy. The same insect, the same mass. Two entirely different outcomes, separated by nothing except how fast it happened to be moving. A SWAT ends it in milliseconds with a barely audible sound. A near-light-speed approach ends an entire neighborhood, with the mosquito itself contributing nothing to the outcome except the velocity it happened to be carrying. None of this can actually happen, and it's worth being direct about why. Accelerating an object with a mosquito's mass to 99.9999% of light speed requires an amount of energy input that no process available on Earth, and few processes anywhere in the observable universe outside extreme astrophysical events, like particle acceleration near black holes, could plausibly generate. This isn't a technology gap waiting on future engineering. It's an energy requirement so far beyond anything humanity, or likely any civilization working within known physics, could produce for an object of this size. The value of the scenario has never been about realism. It's a thought experiment, built specifically to demonstrate, in the most viscerally illustrative way physics allows, exactly how completely velocity dominates kinetic energy once you're close enough to light speed. It's a mental tool for understanding why the speed of light isn't just a very large number describing how fast light happens to travel. It's an absolute structural limit built into the fabric of how energy and motion relate to each other, a boundary that governs everything from subatomic particles to hypothetical insects with equal, indifferent precision. Cosmic rays offer a real-world echo of this same principle, occurring naturally, constantly, in Earth's upper atmosphere. Individual particles, some no larger than atomic nuclei, strike the atmosphere at extraordinary fractions of light speed, generating cascades of secondary particles and measurable bursts of energy, all governed by the exact same relativistic mathematics that would apply to a mosquito if one were ever, impossibly, accelerated to a comparable speed. The physics isn't exotic or speculative. It's already running, quietly, above your head, at a scale small enough that nobody notices. The Large Hadron Collider remains the closest real experiment to this scenario, and its next major upgrade cycles are designed to push proton collision energies even higher, refining measurements of exactly how the Lorentz factor behaves at increasingly extreme velocities. Each experiment adds more precision to a century of confirmed relativistic physics. It will not, and cannot, accelerate anything close to a mosquito's mass to a comparable fraction of light speed. The energy gap between a proton and an insect remains as absolute at the collider's most powerful settings as it is anywhere else in physics. The speed of light will keep functioning exactly as it always has, an unreachable ceiling that turns even the smallest mass into something unrecognizable the moment it gets close enough, and no future collider, however powerful, will ever close that gap for anything larger than what already fits inside an atomic nucleus.